based on a number of a couple of papers I've written on this topic. I'll refer to them in a moment. So as a first observation, let's start saying and observing that firms are increasingly adopting and using algorithms for their pricing decisions. And if you look, for example, on platform and marketplaces, a large fraction of prices are already set by algorithms. And platforms like Amazon somehow emphasize also the benefits of using automation for pricing in terms of source of value and efficiency. And another example I want to mention here, I'll come back on it later on, the company Shells in Northern Europe is now using sophisticated pricing algorithms to set the price of gasolines at gas stations. And they claim to use artificial intelligence. That's an important element that I want to emphasize here. And also, if you just Google word repricing, you will discover an entire growing industry where for little money, you can buy repricing services from these companies. Well, it's a very non-transparent industry so far. Some of these companies claim that they're using sophisticated AI pricing tools. We don't know exactly what is going on, but at least there is a lot of action there. So the point that we want to make here is that pricing algorithms are diffusing, and we think they're not a temporary phenomenon. And in fact, they're not also new in a sense, because if you think about industries like hotels, airlines, and financial markets, well, they've been using pricing algorithms for decades. The type of algorithms that they used was, in fact, what in computer science is often called expert systems. So long, possibly very rich lists of rules of behavior, if then. What I want to emphasize here is instead the fact that the advancement of artificial intelligence generated the possibility of a new class of autonomous pricing algorithms. Algorithms where the programmer just specifies the objective function, for example, profits, which data are fed into the algorithms, what to monitor, and then the algorithms learns autonomously the behavior from the experience. So we're gonna be interested in this second type of algorithms, let's say more modern, and we want to study what is the impact of these algorithms in markets, and in particular on the intensity of competition if markets gets populated by this type of algorithms. So we think there are a number of interesting questions that can be addressed. What is the consequences of AI pricing algorithms on price levels? What type of strategies algorithms autonomously end up learning? Whether they learn to compete or whether they learn to collude. From the title of my presentation, you already can understand where we are going here. What is the impact of imperfect observability on the strategies that algorithms learn? And if they learn to collude, what is the appropriate policy and legal doctrine that we may want to consider in this new, in a sense, new environment? So the talk is based, as was mentioned at the beginning, on a few papers I've written with a group of co-authors. A first paper on AR, and a more policy-oriented paper on science, and a more recent paper on imperfect monitoring. So I will try to give you a snapshot of each one of these papers. Most of the presentation will be based on the first one of these papers. So if you start thinking about the risk of collusion or the risk of these autonomous pricing algorithms being able to coordinate on high prices and collude, Going back a few years ago, some started to worry about this possibility. These two law scholars wrote a very influential book on some of things that can go wrong with artificial intelligence. Some others were somehow skeptical about the possibility of colluding algorithms, referring to some results that we have in economics. I'll say a few words on this later on. Certainly, this debate really was noted by policy and authorities in general on both sides of the ocean. FTC started a public hearing on the effect of pricing algorithms in market. OECD, the European Commission has debated very much this topic. The competition authority in UK has recently written its a position paper. Well, it's an interesting story because they started in 2018 with the first paper saying that the risk of collusion was not so really a real risk. And then they just published this year a new version of this paper where they changed their position. They say, well, perhaps there is something that we need to study more. So in a sense, there was some debate, a lot of talking and conjecturing about the consequences. So we wanted to see whether we could say something as economists on this. Now, if you start, so our idea was, in a sense, very simple. We wanted to study the outcome of repeated oligopoly interaction where pricing decision is delegated to algorithms, and in particular to AI, artificial intelligence powered algorithms. Of course, I will be much more precise on what I mean with this. So if you want to address this type of problem, well, you have some possible approaches that you can follow. Theory. Well, here the problem is that if you want to be realistic on both the economic environment, the market, and the algorithms that can be used, well, it becomes highly intractable quite easily. You may rely on empirical analysis. Here, the problem is finding good data. There is now out one paper that does some interesting analysis on this. I'll say a few words. So what we did in the end, in a sense, was a shortcut. We did some experiments, bunch of experiments and simulations. And so most of us are theorists in this team of co-authors. We somehow used our knowledge of economic theory in order to at least direct these investigations on simulation experiments. So here is what we did. In a snapshot, what we did and the results that we had obtained in this research. So we ran experiments, computer simulations, in fact, with pricing algorithms that are using artificial intelligence in controlled market environments. And in particular, it's going to be a relatively simple, from the economic point of view, iterated oligopoly environment with competing pricing algorithms. So from the point of view, or with the jargon of computer science, this is going to be a multi-agent environment. So there are challenges with this approach, of course. Algorithms must be similar to those algorithms that could be used in reality markets. And the environment, the economic environment, as I said, must be sufficiently realistic. So let me give you a snapshot of the contribution of what we've done. So we somehow dig a little bit into the strategies and documented the strategies that algorithms learned in this environment. We show that AI pricing algorithms have somehow a stubborn tendency to learn collusive strategies in a deep sense. In terms of economic theory, I will clarify what I mean with this. We have shown that these results are robust, also with imperfect monitoring. This is one of our last results that we have been working on. And then we also elaborate a little bit, some reasoning at least into the policy implications. Okay, so this is the plan that I would like to cover. it's kind of ambitious, but I know where to cut if needed. So I will tell you about the type of algorithms that we have decided to use. I will lay down the economic environment and the implementation of the algorithms. A few words on the literature review. I will tell you what type of experiments we have developed, the results, and some robustness, and in particular, these new results on imperfect monitoring. And then few words, really a snapshot on policy. But let me now pause a second and see if there are any questions so far. Okay, so if not, then I move on. So let's talk about the algorithms that I've used for our experiments. So consider this environment. An agent that is an algorithm that faces a sequence of repeated choices over time. For example, a pricing decision, period after period. And this algorithm observes the environment. For example, profits obtained in the past, or prices set by other sellers in the market, and then gets a stream of rewards period after period, which could be the per period profits. So we decided to use as algorithms to explore the class of reinforcement learning algorithms. So these algorithms are designed to do the following thing. I'll be more precise in a moment, but the idea is the following. They are designed to decide period after period whether to exploit. This is somehow computer science jargon. Exploiting for economists would be optimize, given the information, choosing the price that would give the largest possible profit, or instead to explore, using some potentially suboptimal actions just to learn to explore how the environment reacts. Then the algorithm learns from experience, and it learns with reinforcement, which means that as time passes, actions that give higher rewards are used with higher frequency. So more formally, let's put it in.
Sorry, can I ask a question? So should we be thinking largely about kind of more model-free things, where where they need to actually learn the whole environment as well as what the other side is doing? Is that the class of models we should be thinking about? Okay.
Exactly. Yeah. So that's precisely one of the reasons we wanted to use this type of algorithms, precisely because they're model-free. So let me introduce the formal environment, then I'll tell you what I mean for model-free more precisely. So to give a framework to some structure to the environment we have in mind, consider this abstract environment. We will specify it into markets in a moment. So discrete time steps, some state space. So ST is the state in period T, finite state space, finite action space. So the action chosen at time T is denoted with AT. Some scalar per period reward, pi t, and a dynamics described by this distribution, time invariant distribution, which gives you, given the current state ST, the chosen action AT, the probability distribution of ending up in some future state ST plus 1 with let's say end of period reward pi t. Okay, so this is in fact the model. This distribution, this one-step dynamics is the model. So the algorithms that we're talking about here are algorithms that are completely agnostic about the distribution and learn by experimentation how to best behave without knowing this model. So the algorithm is then given some objective, which typically, given our application, would be the maximization of the expected discounted flow of rewards, as you see here. So given some discount factor, And so the idea of this algorithm is to look for the optimal policy, which is going to be a mapping between the state space, from the state space to the action space, in order to solve this problem here. Now, in particular, in this class of reinforcement learning algorithm, we used what is probably the core of this class, which is the Q-learning algorithm. Now, let me specify a little bit more what the Q-learning algorithm is. In order to do so, it's useful to think about this object, which is called in computer science the Q-value function, and to see if you're not familiar with this. So imagine that somehow you were able to back up to find the optimal policy, sigma star. And then, so the Q function is this object that you see here, is essentially the value that you can assign in state S to a given action A. So it gives you the expected current period reward if in state S you choose action A, and it gives and anticipating what's going to happen in the future. Here, the expectation is with respect to the future state S prime. Okay, so in fact, this object, this Q object, is a precursor of a value function. If you take the max of this object here, you just get a value function given the optimal policy. Okay, so the Q-learning algorithm is an algorithm that is designed to identify iteratively the Q function. And once you have the Q function, of course, you can back up from it the optimal policy, which is nothing else the R max of the Q function for any given state. So it's in the class of unsupervised learning algorithm. And the way it works in order to get the Q function and then the optimal policy is the following. So here, in a sense, is a pseudo code of the Q-learning. So you initialize the Q function. Actually, since we are considering here finite state space, finite action space, the Q function is actually a matrix. You can somehow see it as in the rows, the possible states, and in the columns, the possible actions. So the first step of the algorithm, you somehow, in a way, initialize the Q matrix with some values, Q0. And then at each period, the algorithm performs the following tasks. With a given probability y minus epsilon, the algorithm chooses the greedy action in the current state. So the algorithm observes the current state, ST, and chooses on the basis of the information that is stored in the Q matrix, notice the index T at period T, then it chooses with probability 1 minus epsilon, the optimizing action. And instead of the complementary probability epsilon, the algorithm randomizes over all possible actions. This is the exploration component of the algorithm. Then the algorithm observes the news. The news are the per period reward obtained at the end of the period, and the new state ST+1 observed at the end of the period. And then there is the learning component of the algorithm. The algorithm updates the matrix from the information that it had a QT into the updated version of the matrix that incorporates the news that the algorithm has observed. So now let me give you a little bit more details, and I will be done with the description of the algorithms about learning and exploration. So the learning in the Q learning algorithm is performed in the following way. Let's say that a cell in a given period is visited by the algorithm if ST is, the cell with the state S and an action A is visited in a given period if the state is actually the current period state, ST, and the action is the action chosen by the algorithm. So then the algorithm observes as I said, the rewards and the new state, and then the content of this, let's say, visited cell, which corresponds to the cell of the current period, current states and action taken in the current period, is updated according to this convex combination of what the algorithm knew about the value of that action in that state in the previous period, and what the algorithm has learned in terms of news, the current profit, and what the algorithm can expect from the future, given that now the algorithm knows what is the new state, st+1. Okay, so this is the new content of the updated cell. Alpha, the parameter of the convex combination, is called the learning rate. It's going to be one hyperparameter or one parameter of the algorithm. All other cells that are not visited today remain the same. So the content of the Q-learning is unaffected. It's the content in t+1 is the same as the content in t. So you see that by design, the Q-learning only updates one cell at a time. So this is called in computer science asynchronous learning. Last element of the algorithm.
Sorry, can I ask? Can you go back a slide? Is that okay? So one thing I'm curious about here is, should we think of, in the application, should we think of the algorithms as only doing this sort of online learning themselves, or should we think back that someone designing the algorithm could in fact go back and reevaluate this previous sequence of events to change the queue, this transition matrix and this value function? I guess basically it's like, if I can only update one cell at a time, it's quite limiting. Even if in the limit this stuff would converge to the same thing, there may be enormous amounts of arbitrage and pricing that come about by just being able to deviate. Think of it like a filtering problem. You know, I can use a Kalman filter, which is online, but I can then use a Kalman smoother to reevaluate the previous sequence of events. And I'm just wondering if that's a serious limitation of this style of model.
Right, that's a very good question. So sure, it's a serious limitation in terms of amount of time that our algorithm will require in order to converge, as you said. And so the important thing is that we are aware of that. We know that by design is like this. So there are more sophisticated versions of the Q-learning that spread somehow.
Yeah, sorry, to be clear, I don't, the time it takes to converge is not the concern. The concern is that in oligopoly, if one of them has just a tiny bit more ability to game this system by updating two of them, and there's any asymmetry in that, then maybe there's a way to have a permanent arbitrage because it's a little bit smarter than the other one, even if in the end they would converge to the same place. That's my concern in the oligopoly setup.
That's correct. I see the point. We have explored, actually something that we are doing, value function approximation version of Q-learning, which goes in that direction. And so from what I've seen so far, essentially the idea of our results go through, but that's a very subtle point and important point. I will say a few words in the literature review on this. So last piece of information is experimentation. Experimentation refers to the way the algorithm is designed to explore. So there are different ways for exploration that have been proposed in computer science. The most common that we explored, but we also have done other, we have also explored other, used other approaches for experimentation. So the one that I will focus the most is epsilon greedy experimentation. Here, the probability of exploring, that is using potentially suboptimal prices randomly chosen is exponentially decaying with time, t, with this parameter beta, which is called the rate of experimentation. So it's a very simple way to experiment. It's an experimentation that fades away over time. And there is no presumption of optimal experimentation here. And of course, I will say some words later on the implication of experimentation and this type of experimentation. So the reason why we've chosen this Q-learning algorithm is, as we said before, because it's model free. So it's a natural approach to address Markov decision process of the type I mentioned before. Is relatively simple, or is not fancy. So you just need two controls, which is the learning rate and the experimentation rate. Well, actually, you also need the initialization matrix. But that's so we did a lot of experimentation. Let's say meta experimentation on the initialization matrix. Has not so much implication. It works in the sense that if you take a single agent environment, after some time, the algorithm converges to the queue that is associated with the optimal policy. It's popular. It has been used for some of the great success in deep learning. Of course, we are not studying deep learning here, but some of the models. So deep learning algorithms contain as the core of the algorithm the idea, some of them, the idea of Q-learning. And is also successful in game, which is important for us because we are studying markets. Okay, so
before you go on, can you say just a little bit more about what you mean by the state? Because it seems like there's a lot of stuff you're trying to find here. You're trying to find, for example, whether the other competitors are Q learners, things like that.
Right. Can I postpone the answer to this question in 3 minutes, because it's gonna, so the implementation I'm gonna show you will tell you exactly what the states are. So let me give you a brief view of the literature. Computer scientists have already addressed this investigation, this analysis of learning pricing algorithms for markets in some special environments. So in a sense, we are building on these papers, extending to what we think are more relevant, realistic market environment and algorithms. For example, this paper by Tesauro and others, they were using essentially no memory, which is going to be an important element in our environment, and will speak exactly to the previous question on what is in the state. So let me also mention that, of course, there is a large literature of learning in games, where economists have significantly and deeply contributed. So if you have in mind that literature, the main difference that I want to emphasize here is that the reinforcement learning algorithm that we are using here, which is different from the idea of reinforcement learning in the environment of economics used by economists. So the main difference is that there will be active experimentation, as you have seen in the way algorithms are built. And so we will depart from this idea of adaptive or passive learning that has been mostly investigated by economists. And there is also an interesting tight link between the Q-learning algorithm and evolutionary game theory, where, just to give you a map of this link, the exploitation component can be seen in evolutionary game theory, the equivalent to the replicator dynamics, and on the other hand, the exploration component could be captured by random mutations in that literature. Going instead more into the applications that we are studying here, markets. There are other papers doing some experimentation as we did. There is a paper on Cournot, another similar paper on sequential timing, where algorithms decide their prices sequentially. And there is this very recent paper by Asker, Fershman, and Paix, where what they do, they introduce synchronous learning. And the way they do this is by, in fact, related to a previous question, they are introducing some information on the economic model that the algorithm can use in order to update also non-visited cells. So it's a different approach where these researchers are somehow assuming that the algorithm knows some important elements of the economic model, which allows the algorithms to update cells more broadly with respect to what we have done here, what we are doing here. And the last paper I want to, well, there is some literature, somehow limited literature on theory. I will not comment that much on this literature. I would like instead to mention a recent paper by Assad and others that document the adoption of sophisticated pricing algorithms. We cannot claim that these algorithms are exactly those that we study, but adoption of these sophisticated pricing algorithms in the gasoline market in Germany show a significant increase of price cost margin. Okay, so here is the economic environment. I will come to the previous question. So what we are studying,
Giacomo?
Yeah.
Just a question. We've touched on some related questions about the designing the details of these algorithms, right? So it's like, for example, the possibility of doing some smoothing to learn about neighboring cells that are not visited. So these seem to be always asking the question, we're going to fix some set of algorithms in with some specified rules, and we'll see what happens. But now, are we going to be how do we think about the choices of the details of the algorithms, right? So maybe if I use simple Q-learning, someone that's actually doing some kind of smoothing might be learning faster than me. But maybe if they're using that rule, maybe if I deviate to some other type of algorithm, that might be better. So what I'm thinking is, are we going to end up tracing back to equilibrium analysis in some sense of some meta game where players are choosing the details of their algorithms?
Right, that's a very good point. So what I can tell you is that we didn't do this. So we studied our algorithms in self-play. So those algorithms will be in the same class. They will learn independently and decide independently what to do, but they are in the same class. We haven't investigated mixture of different algorithms, and I agree it's a very interesting line of research to see as you mentioned is to study this meta game where we should try to think about equilibria between the class of the algorithms. So the only thing that we have done in this direction, we mixed algorithms that are endowed with different hyperparameters alpha and beta, but still in the class of collude. So the environment that we studied is the following: is an indefinitely repeated game. In the baseline economic environment, there will be just two firms that delegate pricing to algorithms. Commodity goods are differentiated, and we're going to use logic demand, constant marginal cost. Everything is symmetric and deterministic. All prices are observable, so there is going to be perfect monitoring. So each pricing agent repeatedly chooses the price of its product, PTI, with the aim to maximize the discounted flow of profits. So here is, and then sorry, it was more than 3 minutes answering my
question. Sorry, two questions. Sure. First thing first, the state space is discrete, right? So I have a menu, not like a continuum of prices, right? Right. Am I understanding this correctly?
Yes.
Right.
Here is the question. Sorry, here is the answer to your question.
Okay.
So we discretize prices with in the baseline environment just 15 prices. Right? Then we expanded with more prices. The lowest price being slightly below the Bertrand-Nash price, static equilibrium price. The highest slightly above the monopolist price. So here is the discretization of the action space.
And then the other thing that I'm a little bit confused is, where is the source of stochasticity? Is like there's a shock that I know the distribution, I need to learn the moments, or I don't know the distribution and I want to estimate the first few moments. Can you explain that too, please?
Sure. In the basic environment, and sorry for not being enough clear on this, in the basic environment, as I said in the previous slides, everything is deterministic. So the only source of randomness will be the experimentation component of algorithms. So the transition model that I was showing you before in more general terms here is trivial in a sense, because the state, and then finally eventually answering the previous question, the state in a period T is just past period prices of the two algorithms. Okay, so which means that we are endowing our algorithms with one period memory.
So, sorry. So on this, so we have effectively it's a first order Markov chain. Is there any kind of an assumption from the optimization problem in the Q-learning of stationarity of the other side of the transition matrix conditional on your actions? Because in some ways the transition matrix is changing over time. Am I aware of that when I'm solving my Q-learning problem, or implicitly am I taking it as being stationary? And then the second part of that, which I think is related, is that a way to rig trigger strategies with memory? Because if I know that this matrix is changing, does that in some ways bypass the ability to have this one period memory to aid in collusion and things like that? So I think they're related if it's not stationary.
Sure, yes. So here the environment is stationary. The economic environment is stationary. What is not stationary is the presence of experimentation of the other algorithm. But a given algorithm, from the point of view of a given algorithm, the other algorithm is just entering into the state space. So there is really an agnostic view of what is the other algorithm here. If I'm algorithm 1, I just see this component of the state space, P2, that moves around. And that's the way I would suggest to see this environment. And so the important thing is, so you're pointing to an important element here. The fact that the environment is non-stationary due to the multi-agent environment implies that we don't have these general results I was mentioning before for a single agent. First, we don't have general results on convergence, I mean, in theoretical results. Second, we don't have general results on convergence to the optimal policy either of a theory. Okay, so yeah, that's a very good, very important point. So then the exploration probability, so let me go back, is, as I said before, greedy exploration. Just notice.
Can I also ask a question? Sorry.
Yep.
So by specifying the state as past actions, basically, you kind of constrain. So if we have any hope that these algorithms together learn to play some kind of Nash equilibrium of some sort, you're kind of specifying which if they exist, and if they learn an equilibrium, then we're specifying which equilibrium types they would learn, which are the one period memory equilibria, right?
Absolutely. Yes.
Do we know the set of these, or the set of policies that would be played in equilibrium?
No, we don't know. It's too large to. That's exactly the reason why we use this experimental approach. Okay, so
is it fair to interpret this, because the state is the past prices, is a situation in which these algorithms actually know quite a lot about the environment? So they know, as was just said, they know the set of prices, they know the profits. So in a sense, they know at any instant what the profits of some joint pair of prices would be. So it's actually there's quite a lot of information here, isn't there?
Yeah, I agree, Michael. Think about Amazon Marketplace. All this information is available. So if you if you access Amazon Marketplace with your API, you attach to your API your repricing algorithm, this is the type of information you have systematically.
Okay.
So I agree. So we give a lot of information, and that's why also we try to explore the case of imperfect monitoring. Yeah.
So there is a sense in which this overall game has some kind of Nash equilibrium to it. I mean, again, just taking all of the combinations of prices the two firms could set and the profits. So this is evidently because you're going to get something collusive. This is not going to find the Nash equilibrium. Is that
sure.
a good interpretation?
Yeah, that's the point. Yeah. Few notes. We're going to study self-learning simulation. That is, these algorithms are playing against each other. So they are clones and they learn in pairs. It's going to be independent learning. As I said before, for a given algorithm, the presence of the algorithm is totally agnostic with respect to the presence of another algorithm in the market, which just enters into the state, observed state, and there's going to be no communication. I mentioned this because in some modern version of Q-learning, it's also possible to embed communication. So the experiment is going to be what you see here, a large grid of the key parameters, alpha and beta, that we experimented with all these pairs. That we take care with the beta that each cells through the experimentation is visited a significant amount of time. Then we study also many different possible values of delta, the discount factor. I will show you the result for a relatively high discount factor delta. We initialize the Q0 matrix with the assuming that rivals are randomizing. We let these algorithms play up to a very large number of iterations per session, and we run 1,000 session or episode for any of those parameters configuration. So the approach I'm going to take is the following. As we said, these matrices will move around over time, these Q matrices, and then the implied strategy. And so what we're going to do is we wait for these matrices and strategies to stop moving. So we wait for a resting point of the dynamic process, and then we study from there onward. So we study what happens at these algorithms at convergence onward, and we throw away all the learning period, because we want to see, so that's one way to address this issue. We want to see where these algorithms converge. So the results, first, they converge. As I said, there are no general results on this, but in this environment, they do converge. Second, they learn to play equilibrium. I will not have time to go too much into the details of this, but I'll tell you one particular instance of equilibrium play, which is going to be important. They learn to cooperate, which here we mean here that they charge high prices, and they learn collusive strategies in a deep sense. And this learning is robust. So here is for a given configuration of the hyperparameters in the baseline, what would be the distribution of prices that you would observe over these 1,000 sessions. And you see that with respect to the Bertrand-Nash price, the distribution is very skewed to the right. And if you want to see how this maps into profits, well, we define this object, profit gain, in order to normalize the maximal profit gain that an algorithm could obtain as this ratio, the observed profit, pi, minus the minimal profit, the profit with Nash. Remember, we are using also possibly differentiated products, so this profit pi n is not necessarily zero, divided by the maximal profit gain available here, the monopolist profit minus the Bertrand-Nash profit. So if they learn to play Bertrand-Nash, this delta variable, this profit gain should be zero. And imperfect collusion should be 1. So here is the heat map of what we observe. increasing alpha, vertical axis, more updating, increasing beta, less exploration. So in a sense, don't get fooled by the colors. The minimal, if you just randomly pick a combination on alpha and beta, the minimal value of this delta, it's quite high. It goes from 60% to 99%. So well above competitive profits. Now, one important thing here is the following. So did this algorithm just fail to learn to compete? Or did they just actually learn to collude?
Sorry, yeah. Question about the previous picture. So the takeaway is the more they explore, the more collusive the system becomes.
Well, there is a trade-off. It's not really like that. There is a trade-off because more exploration is creating more noise, and more noise makes learning more difficult. And in fact, you see that if you want to have more exploration, you need to reduce updating. It's non-monotone. That's the way. Very interesting insights in this figure, but I don't have time to go into.
Okay, thanks.
So if they fail to learn to compete, well, we just can stop here and go home. Because there will be another algorithm or some smart human player who will exploit this algorithm. If instead they learn to collude, then the thing is difficult. It's more interesting in a sense. So the difficulty here is that these mappings that they have learned, even though the environment is simple, this matrix, the mapping from state into action is a complicated object. So we conceived this idea to study this mapping. So look at this thought experiment. This is a session where the two algorithms have learned to price relatively high price, close to the monopoly price, the green line here, well above to the Bertrand Nash price below here. There are two algorithms, 1 and 2, red and blue. And what we do in this investigation, in this analysis, is the following thing. We force the red algorithm to drop its price for just one period. You see the blue algorithm is taken by surprise, and then we check what they do after this intervention. After this intervention, both algorithms will be free to do what they've learned to do. And this is what happens. You see the blue algorithm that was taken by surprise immediately drops its price, in a sense, dramatically. They stay at low prices for some periods, and then they go back to pre-shock price. So if you want to see how this maps into profits, here it is. So our agent here gets a lot of profits, immediate profit, by, let's say, deviating in our jargon. The blue is taken by surprise, so a disaster. But then the punishment starts, and also the red algorithm has a dramatic drop in profit. So overall, if you account for all these lost profits with respect to pre-deviation, these lost profits are systematically higher than the profit gain of the deviation. And this is just an example, but it's almost everywhere in our simulation. So here, this is telling us that algorithms have learned not only to charge high prices, they also have learned incentive-compatible collusion. So they contain implicit punishments in their learned mapping. And it's not just an example taken for...
Excuse me, Giacomo, can I ask just a really quick question about this?
Sure. Yeah.
So I think this is very interesting, and I can see how this kind of, I don't know how to call this coordination occurs in equilibrium. One thing that this example kind of makes you think about is like, what if this kind of Q algorithm that you have in mind is actually how can I put it, is actually different? I mean, what if these players actually internalize heterogeneity between them? Like if they think about the policies that the other players are playing, like it's almost as if they all think in the same way in equilibrium. And is there room for kind of heterogeneity in response?
Sure. Yeah. That's a very good question. So in the example I'm taking here, they are playing exactly the same prices, but that's just one of the sessions that I've shown you. And in fact, we observe at equilibrium, what we call equilibrium, that is after convergence is taking place, we see a lot of heterogeneity. So we see equilibrium where prices charged after learning has taken place are different. And we also see cycles. So here is just one single price, they converge that. In some other cases, they converge to short cycles.
So can I ask one clarification about that? Are there any scenarios, and I don't know a lot about this, so perhaps not, but are there any scenarios under which there is enough heterogeneity that you can actually diverge and move towards marginal pricing, for example?
I can tell you what we did. What we did here is we studied asymmetric environments with one of the algorithms having a higher cost than the other, and with significant difference. And we do observe very similar effects. Of course, the equilibrium prices would be different. The reactions that you would see here would be different, but they always learn, at least in our analysis, they always learn this type of behavior. So
this coordination is robust to effectively heterogeneity in the agent's behavior, like in the policy.
Yes, yeah. I'll say a few words later on to this. As I said, yeah.
Sorry, you finish. You finish first. Sorry, I just meant to ask a question, but you finish.
Yeah, I just wanted to show you that it's really not a cherry-picking example. So it's always there. Here is also, you see how the price drops for the non-deviating algorithms for any alpha and any beta. By the way, there is a clear correlation between profit gain and the intensity of the punishment or the price drop of non-deviating algorithm. Yeah.
So, I understand. Can you show the previous the picture of the response? Yes. I understand this is an attempt at understanding what is the equilibrium strategy. So what you call deep collusion.
Yeah.
But is there an issue of interpreting this as equilibrium strategy? In particular, if you the alternative, of course, is I mean, from the algorithm perspective, what happened is after this convergence, which means that you have the Q values already for the cells, for every cell, and then you see a new environment. So this is like initializing the algorithm that's not deviating with the equilibrium or the equilibrium Q values, right? You initialize starting from the point of convergence, and you say, okay, observe something else. I'm going to relearn. I mean, there's nothing really about equilibrium. So, I mean, that's alternative. But I understand the continuity here is that the Q values are already in the initial value. Now, look at the deviating one. You force this guy to pick some action. But this algorithm already has the so-called equilibrium Q values. So is this relearning, or is this equilibrium strategy that you're...
That's a very good point and interesting and deep question. So let me answer to this question with a robustness check that we've done. Which is the following. So we as you remember, these algorithms are interacting in pairs. So what we have done is the following. We took two algorithms that learned in different pairs at convergence. We take them at convergence and we match them together in a new market. So then we wanted to see what happened. And it turns out that these two trained algorithms, they start inflicting each other's deviations, but then this part of the learning of what they've learned kicks in, and they're able to restore significantly high price. So this is an extreme version of shock of the type I'm showing you here. So I don't know whether it answers to your question, but so let me go on, because I have some stuff. So how much time do we have?
So we have probably around 5 minutes left.
Okay, good. So
you're welcome to go over though if you need to.
You mean an additional
Perfect.
half an hour? I'm joking. So I just need probably a couple more minutes, no more than that. So let me tell you what we have done. So we explored many dimensions in checking robustness. We made the economic ingredients richer. We complexified the environment. We studied whether these algorithms can end up with fast learning, because as I said before at the beginning, learning is slow by design, given the co-learning I was mentioning in the introduction. And then we introduced imperfect monitoring and in private information on costs. But the message is always there. But profits and prices are way above competitive ones. And we always observe these reward and punishment collusive scheme. So let me skip most of these extensions. Just to mention that we studied longer memory that is endowing the algorithms with two-period. Sorry, the state then is defined as the prices for the past two periods, and still results are there. These more clever algorithms don't do necessarily better because then the Q matrix is much larger, as you might imagine, and then learning requires more time. Let me spend a few last minutes on imperfect monitoring. I guess you are familiar with this Green and Porter paper, where here I switch from price competition to quantity competition, as in Green and Porter paper, where demand is stochastic, can be just high and low, and firms, they observe the realized market price, and goods are perfect substitutes. Okay, so each one of the algorithms now, instead of choosing price, it chooses quantity, and they observe price. So the state now for algorithm I is the past period price and chosen past period chosen quantity, but the algorithm does not observe the quantity chosen by the other algorithm. That's the imperfect monitoring component. So the difficulty here is that if you observe a drop in price, this could be the outcome of a negative shock on demand, or it could be the outcome of the other algorithm having flooded the market with larger quantity. So we observe exactly the same high profits, low quantities here, and rewards and punishment scheme. And the interesting thing here is that if you think about the solution that the Green and Porter gave in their seminal paper as a strategy that supports supra-competitive profits, is the idea of a strategy that sets a threshold price below which the players, for some capital P periods, they start a war, they flood the market with high quantity, and then after capital T periods, they revert to pre-deviation output. Now, if you think about these algorithms, they don't have long enough memory, no? Because, for example, suppose we endow them with just one period memory, one could be much too low with respect to capital T. The interesting thing is that they somehow circumvent this limitation and generate a surrogate clock of this length of punishment. And the surrogate clock comes from the intensity of the punishment. So the first period they punish harshly, and then period after period, if nothing changes, they punish less and less, and then revert back to pre-shock quantities and prices. So let me just conclude with really the last 2 minutes, 2 words on policy. Now, as economists, we are used to teach to our students tacit collusion as precisely this reward and punishment scheme I shown you before with my previous graphs. But if you look at application of collusion in antitrust courts, then if you don't know, you will discover that what is currently forbidden almost all over the world is not tacit collusion, it's explicit collusion. And courts and authorities and judges, they must rely on what is called hard evidence in order to make a case of collusion. That requires essentially explicit communication. Now, if you take literally our results into real markets, then this tacit collusion will never be, so will always be lawful, considered lawful according to the current legal standards. So then what should we do with that? And we try to discuss a little bit in this short science paper what are, in our opinion, interesting avenues to address this difficulty. And then I'll conclude, the idea is to exploit a material difference between algorithms and humans. In this table, you see probably what are the most relevant difference in terms of ability to collude. So communication for algorithms, as to some extent we have seen, is not needed. On the other hand, for humans, it's one of the most important elements in order to have cooperation or collusion to emerge. That's why one of the reasons why authorities rely on it. Now, collusion pricing rules or strategies are latent or non-discoverable with humans. If you go to a manager who run a cartel and you ask, tell me what's your strategy, and I want to see whether it contains this reward and punishment scheme, then this is not discoverable, of course, because it will never tell you. On the other hand, you can audit algorithms. You can somehow look inside with the type of exercise that we have developed and shown you before, and discover the learned strategies. And so we think that exploiting these ideas may help somehow prepare. So we are not pushing here authorities to find solution to what we have discussed and found in this research. We still think that probably it's too early to act in terms of policy, but we do think that it may be interesting actually to interact with the multidisciplinary research between law scholars, economists, and computer scientists to find a solution to this type of problem. And then I'll stop here.
Great, thank you very much, Giacomo. We're a little bit over time, so maybe we have time for one question. If someone has one last question.
I can ask a question.
Yes, Mary, please.
Yeah, Giacomo, so let me get this completely understand this. So the agents know the payoff their actions, the functional form, right? Like they don't?
No, not the functional form. That's why the model free. So they just at the end of the period, so they start of the period, they choose an action, and at the end of the period, they observe the profit. That's it. They realize profit. So the algorithm has no knowledge, no notion at all of the profit function.
Oh, okay, so that's okay. So it's not a planning problem anymore.
No,
okay,
absolutely.
okay,
Right. Yeah.
Yeah. Thanks.
Great. So thank you very much, Giacomo, and thank you very much, everyone, for coming.
Thanks to you for attention. Thank you.